more efficient, but also smaller and even lighter. The core value propositions actually of the technology are very clear: increased energy efficiency, reduced size and weight, and superior thermal performance, all of which contribute actually to a reduced overall system cost. So, um, uh, we are seeing that GaN is already being available and replacing the traditional technologies in a wide range of applications, including home appliances, drones, robots, adapters, chargers, and as well as the switch mode power supplies over in the data center world. The market, the GaN market, is experiencing rapid growth with a CAGR of 47% from today, 2025, to 2030, actually, and a cumulative market potential of approximately $8 billion over the next 5 years. Now, this accelerating adoption is driven by a powerful economic and engineering synergy. While the GaN transistor may have a higher unit cost than the legacy silicon MOSFET, the ability to switch at higher frequencies allows us to use even smaller, lighter, and more cost effective passive components like all the capacitors and inductors we need on the PCB. And this reduces, the higher efficiency of GaN reduces the heat dissipation, lead us to even either smaller heatsink or heatsinkless designs. And this combination of superior performance and a lower overall bill of material for sure gives us a complete system that is kind of fueling this market growth. Now, when we compare power semiconductor technologies, a key set of metrics known as figures of merit are usually used to quantify the performance. And these figures of merit combine the R on or RDS on, the on state resistance, with a measure of on the device's parasitics. Energies and charges. Now, a lower figure of merit value indicates a better performing device. This table on the screen provides a detailed comparison of our GaN 650 volt G5 transistors against comparable silicon carbide and silicon devices based on their figures of merit. So the first figure of merit we'll look at is the RDS on times USS. And this is related to the energy actually stored in device's output capacitance. A lower value signifies reduced switching losses in hard switching topologies, such as the classic boost PFC converter. Now, the second figure of merit is the RDS on times QG. And the gate charge, which is the QG, represents actually the total charge required to turn on the device. This figure of merit directly impacts the gate driving losses, which is critical for high frequency operation and light load conditions. As the table shows, GaN has significantly lower value, enabling higher efficiency by reducing these driving losses. RDS on times QSS is another figure of merit as well. And this figure of merit relates to the stored energy in the output capacitance when the device is off. A lower value enables better performance in soft switching topologies, such as the LLC resonant converter. Reduced energy in the output capacitance allows for a faster and more efficient transition, which is also some enablement for us to use a smaller passive component and leads us to increased power density. And arguably, the most critical and differentiating figure of merit of GaN is the RDS on times QRR. The reverse recovery charge is the charge that flows in the opposite direction when the diode is forced to turn off. Now, for silicon and silicon carbide, we've got the physical p-n junction that acts as an intrinsic body diode, which incurs a significant reverse recovery loss during commutation. But because GaN transistors do not have this physical p-n junction, they exhibit zero reverse recovery charge. And this is a game changer, as it allows GaN to be used in topologies with repetitive commutation, such as the CCM, the continuous conduction mode, Totem pole PFC, with minimal losses that we can get. So, the superior figures of merit of cool GaN translate directly into the performance improvements at the system level. And that's a graph that presents and shows a clear performance advantage for GaN over other technologies. The efficiency curve demonstrates that cool GaN enables the highest efficiency across the entire power range at increased switching frequencies. And the bar chart comparing power dissipation provides a powerful visual for the quantified reduction in the losses. Now, it demonstrates that GaN has a significant advantage with more than 50% less power dissipation compared to silicon solutions. Now, this reduction in the power loss is distributed across several components, including the diode turn off, switch turn on, and turn off, and conduction. The low switching losses are a direct result of the GaN's fast turn on turn off speed and its minimum switching losses, which are fundamentally linked to its very low gate and output charges, as we already explained. And this high efficiency and lower power dissipation ultimately give us um, a, a, a system that is higher in power density, simpler, and in most cases, more thermally managed for a final product that we need. Section number 2. So, the totem pole PFC topology is an excellent example of how GaN's unique properties enable new high efficient circuit designs. So, a classic PFC stage uses a lossy diode bridge. That bridge rectifier at its input. This diode bridge incurs significant conduction losses, particularly at high power levels, which necessitates bulky heat sinks and limited overall efficiency. By contrast, the totem pole PFC topology eliminates the input diode bridge, and it uses a half bridge of GaN on the high frequency leg and other two slower, lower cost silicon on the lower frequency leg. This architecture is only practical with GaN that provides and that lacks the physical p-n junction, and during the switching cycle, the high frequency GaN must commutate current from one another, and in this way, we don't have this intrinsically body diode, and then we've got no losses, and the losses are all eliminated, making the totem pole PFC not only viable but a superior choice for high power, high efficiency applications. Worth mentioning is also the lateral structure and or the lateral operation of the GaN transistors. So the lateral operation of the GaN transistors, that is a consequence of their two-DAG channel, allows for the monolithic integration of multiple devices on a single chip. And this architectural choice is fundamental for an entire product roadmap. We'll speak about it later on. And that's towards a higher integration and system level cost reduction. The compact monolithic device that can block high voltages in both polarities is highly beneficial for applications such as solar and high power SMPS, where the bidirectional power flow is really needed and is often required. So, a monolithic bidirectional switch, BDS, can replace two discrete powered switches configured back to back with a single device. And the benefits of this approach is that it offers a significant area and cost advantage, potentially a factor of 4 over the conventional vertical MOSFET switches, and results in 50% PCB area gain and 50% reduction in the BOM for the switch stage. This level of integration not only simplifies the design, but also significantly reduces the parasitic inductances, as the internal connections are orders of magnitude shorter, really, than external bonds on the PCB traces. And This as well enables designers to create new topology concepts with higher performance, which directly addresses the market demand now of higher efficiency, higher power density, and lower cost. GaN switch selection. So in order to select a GaN switch, you've got four main key factors. We'd go into them into details. Switch type, on resistance and paralleling, packaging, and device models. Once you've got the topology and the switching frequency identified or defined, the next step is to select a specific GaN switch. Now, we offer a family of high voltage GaN switches and medium voltage GaN switches based on E-mode technology, and which means they are normally off and require a positive voltage to turn on, ensuring a fail-safe state. And that's usually a type of switch that has more advantages as compared to the cascode GaN. We'll keep this discussion for later stages, but for now, I can ensure E mode is better. The specific architecture of Infineon's cool GaN is the GIT, or what we call gate injection transistor, which features a p-doped gate with an ohmic contact. This results in a non-isolated gate with diode-like input characteristics. And while this is a departure from a standard silicon MOSFET gate, it offers a robust solution for a normally off-power switch. And this architecture really facilitates advanced integration, leading to products like CoolGaN Drive Family, which combines two switches and their dedicated gate drivers in a single compact packaging. The second factor is the R on, and the RDS on is really a key parameter in the switch selection. The fundamental or the trade-off is always is balancing the conduction losses with a reduced or a lower RDS on, and balancing with the switching losses, which typically increase with the larger devices and higher capacitances. An optimal solution is always um, looking at the power profile and the duty cycle. Now, at Infineon, we provide a wide range of CoolGaN products with RDS-ons ranging from 25 to 450 milliohm. For applications as well that need even lower RDS sounds, paralleling two or more switches is always a viable option. So, and GaN and the cool GaN of Infineon is particularly very well suited for this strategy of parallelism, because because the on resistance has a positive temperature coefficient, and this means that if one parallel device begins to carry more current and heat up, its R on will increase, which naturally forces a more even distribution of current among the parallel switches. This self-regulating behavior ensures a reliable and a stable operation without any complexity when it comes to balancing the circuits. And another as well. So the third factor is the packaging for sure. Thermal and electrical performance are intrinsically related to the device's package and to the PCB layout. So Infineon GaN switches are available in variety of packages. Um, you've got the die pads exposed for effective cooling, either from the top side or from the bottom side. So you've got top side cooling, bottom side cooling packaging. You've got a critical consideration in the high-speed GaN design, which is the parasitic inductance, and this inductance is shared by both the power loop and the gate loop. So during any fast switching transient, the high rate of change of the current, which is the di by dt, in the power loop induces a voltage across the mutual inductance and opposes the gate drive voltage. And this actually slows the switching speed, increases the switching losses, and can cause any voltage spike in your system and can cause ringing. So in order to address this, all Infineon's discrete GaN products feature a Kelvin source connection. Now, the Kelvin source pin provides a clean, separate reference for the gate driver, effectively eliminating all the negative effects of the common source inductance and enables the device to switch at its fastest possible speed. Now, using the Kelvin pin introduces a new design constraint because the voltage at the main source can swing hundreds of volts during a switching transit. However, the gate driver's input and output must be isolated to protect the low voltage control circuitry. And finally, device models. So in order to accelerate the device process and ensure reliable performance, accurate device models are really essential. Infineon provides a comprehensive models for its cool GaN products that are compatible with common electric simulators like LT-Spice or Symmetrics. These models are just are more than just only representation of the switch. They consist of four key components: electrical module of the inner switch, where you've got the transconductance and capacitances. You've got the package parasitics in the terminal inductances. You've got the thermal package module. You've got the electrical gate drive module. And when all this is combined with your estimated PCB parasitics and the thermal parameters, these models would provide you a high accurate simulation environment, will allow you as a designer to predict the switching Fourier forms, to calculate your losses, to validate your chosen system concept, and do all that before even committing to building a physical prototype. Section number 4, driving GaN. While GaN switches have a much lower gate charge than silicon devices, which is approximately 10 times lower, making them easier to drive, the specific characteristics of the GIT architecture requires a dedicated driving approach. Um, because the GIT's gate behaves like a diode, a standard low impedance MOSFET driver would cause a high variation in the gate current. So the solution is a simple circuit, is a simple interface circuit consisting of a couple of capacitors and resistances, and that's called the RC interface, allowing the designer to control the turn on, turn off, and the steady state holding current of the gate, where you will get a standard quasi-ideal driver such as those we provide at Infineon's ICE drivers family. And we'll get to the portfolio of the ICE driver in a second. Now, the gated drive supply voltage must be carefully chosen. GaN transistors have a low threshold voltage, typically between 1.2 and 1.5. While this low threshold contributes to the efficiency, it also makes the device more susceptible to unintentional turn on due to the voltage transients. A common solution to mitigate this risk and ensure the device remains safely off is to apply a small negative voltage to the gate during the off state. The optimal gate drive voltage depends on the specific topology. However, the recommendation is 8 volt to 12 volt. For high switching applications as well, a few volts of negative gate drive is typically needed, and this can be generated using any bipolar power supply, or more simply through the RC interface that is coupled with the capacitance. The decision as well of whether or not to use Kelvin source is crucial in your design based on your application. And for hard switching applications where the goal is to achieve the fastest possible switching speeds and minimum losses, using the Kelvin source pin is strongly recommended. The Kelvin source connection effectively eliminates the common source inductance, which would otherwise slow down the switching transition. And as we previously noted, this requires a gate driver with isolation, as the voltage difference between the Kelvin pin and ground can swing significantly. Now, conversely, for a soft switching applications where devices are switched at or near zero voltage, a small amount of common source inductance less than maybe 1 nanohenry can actually be beneficial, and that this will serve to slow down any unintended hard switching transits and will help reduce the voltage stress on the device. And in these applications, it's generally recommended to either leave the um, Kelvin pin open or connected to the main source. This design choice provides a tangible example on how a deep understanding of GaN's behavior in different topologies can lead you to an optimized system performance. We offer a broad portfolio of gate driver ICs for the GaN market, and our family is called the ICE Drivers family. I invite you all to have a look at the portfolio and check the website. Um, the portfolio includes both one channel and dual channel configurations with variety of isolated and non-isolated options to support all the application needs. Um, in the portfolio, we've got multiple characteristics like the high common mode transient immunity, the optimal gate drive current, the fast and accurate propagation delay, the under voltage lockout, and this table really summarizes all the portfolio that are a perfect fit for the GaN device, for the GaN design. We won't stop here a lot. I also invite you to check all the data sheets and all the evaluation boards where you can evaluate GaN and Infineon's drivers together so that you've got hands-on experience before you go to your prototyping and design building. PCB layout. So the PCB layout is a crucial part of the design. It plays a critical role in the overall system performance, particularly in the thermal management. And many physical parameters of a GaN switch are temperature dependent. That's very important. But of particular importance is the RDS on, which can increase roughly by a factor of 2 at maximum junction temperature of 150 compared to its value at 25 degrees. So any increase in RDS on directly leads to higher conduction losses, as we know, and reduced efficiency. Um, Therefore, keeping the switch junction temperature as low as possible is always beneficial, as it minimizes the conduction losses and energies dissipated and ensure that the system is reliable and could operate for a long term. An effective PCB design and layout with large copper pores and proper heat sinking is essential for also minimizing the thermal resistance and ensuring the device operates within the optimal temperature range. Parasitics, again, parasitic PCB inductances and capacitance are a primary challenge in the high frequency designs. The power loop inductance is the most critical. With the extreme high di by dt that we can achieve, even a small parasitic inductance can play a significant voltage overshoot and can damage the device. So a design guideline, the power loop in combination with the design's input capacitance forms the LC oscillator, and that's always a concern. A design guideline, in the design guideline we say the power loop inductance should be kept below 10 nanohenry. The gate loop inductance is also a concern. The gate loop in combination with the device input capacitance, they form this LC oscillator, and this can lead to any ringing and usually, damping resistors are often required to mitigate this ringing. The high side gate to ground capacitance should be also minimized to reduce the risk of cross conduction. Integrated solutions like GaN drive products are designed always to minimize both the L loop or the power loop inductance and the LG, which is the gate inductance by design, simplifying the layout challenges that a designer could encounter. And here I would like to stop a little bit on our portfolio. So the CoolGaN bidirectional switch is the groundbreaking monolithic GaN device designed to enable all the new topologies and simplify the existing ones. And unlike any conventional approach, um, that require 2 or even 4 discrete switches back to back configured, the CoolCam BDS is a single device that can block voltage and conduct the current in both directions. And this unique architecture gives the lateral structure of GaN. Leverages the lateral structure of GaN to use the same drift region for voltage blocking in both polarities. And this significantly reduces the die size compared to the conventional arrangements. The BDS simplifies the design, reduces the BOM, enables new topologies, and higher efficiency and power density, making it really a compelling solution for our next generation power converters. I also invite you to check on the website. We've got samples available. We've got the data sheet on the website. That's a huge turn on in the marketplace. We also for sure offer a broad and continuously expanding portfolio of the high voltage cool GaN transistors, where we provide the designers the opportunity to have an optimized product for their applications. This portfolio includes devices with RDS on from 25 to 450 or up to 500 even milliohm, in multiple packaging, including ThinPack, DFN, DSO, GSC, TOL, TOL-T, DPAC. And this portfolio table here provides a clear overview of all the available devices at 650 and 700 volt, categorized by package type and the on resistance. You've got a breadth of choice, ensuring that you can select the device that perfectly balances the performance, the thermal management, and the form factor requirements you need for your application. And to end up, I would like really to sum it up and give you the very crisp key takeaways. We are leading with robust silicon carbide, and GaN portfolio. The Cool GaN of Infineon offers advanced switches and a variety of families of devices with optimized on resistance and the type of cooling you need, bottom side, top side, and dual. The comprehensive design ecosystem supports the GaN integration. Our ICE drivers, ICs optimize the gate driving for the GIT type GaN transistors we've got. The BDS, which is the monolithic BDS, simplifies the designs and boosts the efficiency. And our strategic focus is driving the influence in a projected $8 billion GaN market with a 47% CAGR. With this, I would like to close the session. Thank you for the attendance, and we meet each other in the future, very near future, with even more webinars. Thank you very much.
Well, thanks, Amira, for that great presentation. Okay, we already have several great, interesting questions from our audience, but I want to let you know that there's still time to submit questions. If you want, just go to the Q&A tab that you see on your right-hand side of your screen. Okay, Amira, you ready to answer some questions? Okay, here we go. First question. The question says, sorry if this was mentioned, but does Infineon have plans for GaN HEMTs rated for even higher voltage, for example, 1 kilovolt or plus?